all about landslides. So we're going to switch into slope stability and landslide processes. And again, please keep the questions coming real time in Zoom. Raise your hand at the end or use the Google chat. Really appreciate everyone being here. Pop in, pop out as you can. The rest of the schedule is posted on geoclash.org. If we want to maybe put that in the links again. And I did see there's a few questions about QStar, and Francis, thanks for getting back to David about that. So this is exactly what we were hoping, have some good exchange. So I'm going to pass it to my colleague, Dimitrios Zekkos, who is running the slope stability session. Thanks, Dimitrios.
Yeah, thank you, Josh. I enjoyed a lot the previous session. I'm excited to help moderate this one. So welcome, everyone. And in this session, we'll be talking about landslides. And so let me share some slides very briefly about this. So you may have noticed, first of all, that this session will last, I'm hoping you're seeing my slides. You may have noticed that this session will last for an hour and a half. We had lots of different types of presentations related to this topic. So we decided to expand the duration of this session to give us a little bit of time also for discussion. I wanted just very briefly to make sure that you all recognize how this session fits to the previous ones and to the whole cascade. This is again a figure we've been using in our vision. And yesterday we heard a lot about excellent presentations about critical zone and what's happening in the near surface. And then we started talking about forcings, like the geologic forcing, tectonic activity, and then also the environment from above, precipitation, temperature, and how this affects that zone. So we have a system that is responding. And in some cases, the environment is super cold, and we talked about that, about cryosphere processes. And today we've been moving, this is really sets the setting. And then we have in this system, based on these forcings, we talked about hydrology and flood routing. This was just completed now. And now we're going to talk about the impact of all of these forcings on the system, and which basically landslides and slope stability. The next session is also tied to this, because when you have these systems, you have sediment transport. And of course, this affects the processes before they affect the system itself. And finally, we're going to have exposure and risk. So it's all it's almost presented as a linear process here, but of course, it's not a linear process. So what we'll do today is that we're going to have 9 7-minute presentations, and we know these are very tight presentations. But the purpose of this session, as has been said before, is more to get a feeling of where the state of the art is, just get different perspectives. We're going to have also a 15-minute discussion that we absolutely recognize is not enough. But again, this is a reminder that this whole 2-day event that we're doing is a preparation for a more in-depth session on modeling later this year. So we're going to have a 7-minute presentations, and I just use green colors here to see about the different types of instabilities we're talking about. We're talking about shallow landslides, deeper landslides. We're talking about debris flows. We talk about ground failure, about rock slides and avalanches. And so we have a whole range of landslides. And here we have also a number of stressors. There is a number related to rainfall, post-fire. You don't see too much earthquake here, but there was a session on that yesterday. And so, of course, earthquake is part of the whole system that we're looking at, and even tsunami. And so there are a couple of presentations also that bringing also the monitoring and the hazard assessment part of it, which I think is really, really exciting. Again, I want to remind you, all the speakers, that as you give your 7-minute presentation, think about these questions that we have been thinking about all this time, about the opportunities for coupling, specific challenges associated with modeling and the gaps. And then, of course, there are going to be more questions related to more maybe the details of that. All right, I think with that, I don't want to spend more time on this. I would like to introduce the first speaker and welcome the first speaker, which is Luke McGuire from University of Arizona. Luke, you want to get going?
All right.
Awesome.
Well, thank you all for organizing this and for the opportunity to speak today. I'm going to talk about some process-based modeling of runoff-generated debris flows following fire. And my main objectives are to give you all an idea of first the conceptual model for how these debris flows get started, and then briefly describe a process-based numerical model that we use to simulate these processes, and give a few examples of how the model can be applied to inform our understanding of debris flow hazards. So one of the more recent examples of an impactful post-fire debris flow happened following the 2017 Thomas Fire in Southern California, when the Santa Ynez Mountains, shown here on the left, located above the community of Montecito, were burned at moderate to high severity. There was an intense band of precipitation that moved over this part of the burn scar, and it led to a series of debris flows that then moved down over a populated alluvial fan and led to the destruction of a number of houses, as you can see here, and more than 20 fatalities. So debris flows are much more common in the immediate aftermath of fire for a couple reasons. One is that there's sometimes fire-enhanced water repellency that can reduce infiltration capacity of the soil. The fire greatly reduces canopy cover and ground cover, which can lead to more runoff and erosion. And when we have extremely steep landscapes, then when all of those factors combine, we tend to get rapid mobilization of sediment on steep slopes as surface water runoff collects in rills, gullies, or low-order channels, and that can lead to the development of these debris flows. So you can imagine that a model designed to simulate all of these processes would need to include infiltration, runoff generation, and then the subsequent routing of that runoff across the surface. It would also have to account for detachment and transport of sediment from a variety of areas, because debris flow sediment in these post-fire environments can be sourced from a number of locations. Some of that sediment may come from divergent areas and interrill areas on hill slopes. Some of it's going to come from rills and gullies, and some of it's going to be eroded out of channels. The model inputs then would be things like rainfall, and ideally a time series of rainfall intensity, a rainfall hydrograph like you see here on the left, some information about the severity of the fire, because that greatly affects ground cover and soil burn severity, which can be estimated using remotely sensed products, and then ground truth has a large impact on soil properties, including its erodibility and the soil hydraulic properties that control rainfall runoff partitioning. So we need information about rainfall, burn severity, topography, and soil. And the outputs for this model are temporal variations in flow depth, flow velocity, and sediment concentration across whatever landscape we're modeling. Normally, we run these simulations at the watershed scale because we're interested in trying to understand which watersheds might be more or less susceptible to debris flows compared to others, which watersheds are going to produce large debris flows, which ones may produce just small debris flows, and how does that debris flow susceptibility change through time. So to give you an idea of what I'm talking about in terms of inputs and outputs, this may be the type of simulation that we run with a small watershed here, about 0.01 square kilometers. We have some input rainfall hydrograph, and the red line shows how we progress in time through this storm. And initially, as we solve this series of PDEs that govern conservation of mass and momentum of the water and sediment as it moves across the surface, early in the storm, there's very little, if any, runoff, because the soil is able to infiltrate all of the water that's come down as rainfall up to that point. Once the rainfall gets more intense, then we start to generate runoff. That runoff converges into rills and gullies, and you start to get sediment entrainment, which I'm not showing here. And then as the storm progresses and the rainfall intensity decreases, then again, you get subsequent reductions in flow depth. And we're usually trying to summarize this information in some way to make it more digestible. And one thing that we look at is what happens at the watershed outlet. What's the flow depth and how does it vary over time at the watershed outlet, in this case shown by this yellow star. You can see this is a small watershed, so our peak flow depths are relatively small. on the order of 20 centimeters. But since this model also accounts for erosion, deposition, and sediment transport, we can track changes in sediment concentration over time at the outlet. And when we see sediment concentrations above 0.4 or 40% by volume, then that's usually indicative of getting debris flows. So you can see here that there are several periods of time during the storm where we had constant sediment concentrations that approached levels we would expect in debris flows. And we can summarize this information further by looking at things like, well, what's the volume of debris flows that came out of the outlet of this watershed? How does that vary with things like rainfall intensity? And so on the right are a series of hyeta graphs with different values of the peak 15-minute average rainfall intensity, which I'm denoting here as I-15. And so you could think of this as being associated with different design storms, maybe like a one-year recurrence interval storm versus a 5-year versus a 25-year. And as your rainfall intensity increases, as you might intuitively expect, you see increases in debris flow volume. Now, these simulations were all run with vegetation and ground cover conditions and soil properties that are associated with immediate post-fire conditions. But of course, these landscapes are very dynamic, and vegetation comes back and soil recovers. And so one of the nice parts about having this type of process-based model that can ingest things like soil hydraulic properties that you can measure in the field, vegetation cover that you can get from remote sensing data, is that you can incorporate that back into the model to see what's having the biggest effect on changes in debris flow susceptibility and debris flow size over time. And just an example of that is illustrated here, that you can see as we move from post-fire year 1 to post-fire year 2 conditions, we get a large drop off in the debris flow volume. So these are the types of ways that we apply this kind of model. So with that, I'll leave a few kind of conclusions up here, but again, just thank you for the opportunity and really enjoying the session so far.
Thank you. Look, this is a very interesting presentation and also very well laid out. Thank you so much for getting this conversation going. Again, I remind you can type your questions either in the chat or in the Google file to Luke or to anyone else. I know Luke will have to eventually go because he's teaching a class. So if you have specific questions for him, maybe you can ask him now. The next presenter is Ning Lu from the Colorado School of Mines. Ning, thanks for coming over.
All right, so can you see my screen?
Yes, yes.
Yeah, thank you for the opportunity. Today I'm going to share with you the development we have been working on for the last 2 decades on the predicting the landslide due to the precipitation. And as we know that due to the climate change, we have the atmospheric river in North America, this particular Pacific West Coast, and the stream will come to hit the land. As they do so, the temperature is going to drop, and then the humidity is going to increase and cause a different kind of a precipitation, whether it's a snowfall or rainfall. And that can cause a landslide or trigger landslide. What you show here is the in Southern California back to 2005 El Nino year. Just a little bit more precipitation than a normal year. It's going to cause this vast shallow landslide. So the framework we're going to build is basically try to capture the governing variables and to be able to use the meteorological data, use the subsurface hydrological mechanical property to be able to predict the landslide as such. So we're looking for the information. The 3 pieces very important information. The first one is the meteorological information, as you showed that here is the back to 2005. We can get the precipitation, and then we also need to monitor, understand the subsurface response. In this case, the hydrological response. 2 variables. One is how the soil moisture is going to change. The other one is how the pore pressure. In the case of above the water table, it's what we call a soil suction. And the process that we look at here is from the rainfall precipitation, we monitor the soil moisture. We also monitor the soil suction. But there is always an important relation between the soil suction and soil moisture, and that what we call the soil water retention curve, which is attached to each different soil. And that can be characterized in the under the in situ condition as well as the laboratory condition. The more important is the response of the mechanical. Slope will fail because of the mechanical that reaches some kind of thrustful or the strength of the hill slope. And what particularly important for the material like the variable saturated is the effective stress. And the part of the effective stress we call the suction stress. And this is also the characteristic for soils, and we call suction stress characteristic curve. And with that one, we will be able to understand and characterize, quantify what will be the so-called effective stress, which is the one that holds the slope there. And when the effective stress reaches some threshold, or we call the shear strength, and it's going to have landslide. So this is basically the entire process. Is we try to understand, try to quantify the soil moisture, the suction, and try to quantify the effective stress. And we come up with the ability to see whether we can predict the landslide. What I'd like to elaborate here is the two constituent equation, which is very important. That can be characterized under both laboratory conditions. We take the soil sample, or we can also do in situ. We can use monitoring data to back this. Very important. One is the hydrological to control the soil water retention or interaction, and that is under the principle of the energy equilibrium. The other one also is very important is how the ultimately slope is going to sustain for the stress, and that is so-called suction stress that can be characterized from here as shown by the soil water characteristic curve, because we find the relation between the two of them and to share the common physical parameters. And with that, we come back to here is how we can build that. So we would need to know that the framework, we need to know the geomorphological information at the topographic, the geology. And we also need to know hydrology, which is the precipitation. And we also need to know the response. And once we know that, we can hydrological response. And then we can also use the information to quantify the mechanical response, which is the stress distribution. With that one, we'll be able to predict whether landslide can occur. So it put into this diagram is the ultimate goal is to understand or to predict the initiation when the landslide is going to occur. So we start with the information of climate and the material property of geological and topographic, and we can understand how the water is going to go into the hill slope with those information. We solve the so-called equation mass conservation, and we will be able to know the distribution of the suction and the moisture content for a particular slope or interest area. And then we also can run the mechanical model, which understand the stress, background stress due to the tectonic, due to the soil soft weight, and also the hydrological. More important is the hydrological induced due to the rainfall. So the ingredient here is one of the very important is the hydromechanical that will have a couple of them. The second is the build effective stress, which is translated basically the information from hydrological to mechanical. And those effective stress is going to determine whether slope is going to be safe or not, or stable or not. And we also implement a new way to understand is to define the so-called factor safety. And here we are doing the factor safety for every point because we can understand the hill slope stress distribution, soil moisture distribution, and suction distribution. Let me give so what are the parameters we really need for the model to run? And here is the classical one that we usually would be able to know. We need to know the hydraulic property of hydraulic conductivity, and we need to know the soil porosity. We need to know the strength parameter, cohesion friction angle. But it's a new framework that actually expand that one from saturated to unsaturated or variable saturated. I just need to have a few parameters which basically characterize both soil water characteristic and hydraulic conductivity function. So we've been doing that in the last 2 decades using the real data and to calibrate the real data from the field scale as well as doing the laboratory study. What I'm going to use an example to do the model prediction is in the East Coast of North Carolina under the hurricane. So if you go back to the hurricane, the Francis and the Islands, back to 2004, the events actually hit North Carolina and has a lot of landslide. Very interesting is these 2 sequential hurricanes. And this
Dr.
is
Dr. Liu, we'll have to ask you to wrap up.
yeah, I will have okay, yeah. So this is the period that where the precipitation is, and then you can see that the first hurricane will hit North Carolina, and then the second one after stop about 6 days, and it will come to that. So we can use the model information of the precipitation, use the understanding of hydromechanical to simulate that one. What I show you here is the process of the. You can see how the stress, pressure, distribution, as well as the failure. What you see here is the failure evolution. And the second one, particularly when it hit it very hard, and then you can see the landslide occur. So I'd like to wrap up the key point of what I try to say here is the hill slope occur under the variable structural condition, and it can be analyzed with hydromechanical framework. What's important is they're both hydrological and mechanical, and hydrological will control the energy equilibrium, and the mechanical will control the mechanical stability. And we can link that two together to analyze the slope. And particularly, we use the local factor severity, so we don't need to presume that failure surface that it will be predicted. And we have continue to conduct a case study and use that one to build a better model. Thank you.
Thank you, Ning. This is excellent. Very lots of good content and discussion on unsaturated soil mechanics and the impact on landslides. We'll move on to the next presenter, which is Ben Leshchinsky from Oregon State University, who will also talk about precipitation-induced landslides.
Thanks, Dimitrios.
Ben?
Do you hear me
Yeah.
okay?
Yes, we can hear you well, and we
Great,
can see the
great.
presentation. Yeah.
Okay, thanks. Thanks so much. And thanks for having me. So my name is Ben Leshchinsky, but I'll be presenting the work of a lot of great grad students and collaborators, just being the messenger here today. We'll be talking about inverse analysis of landslide inventories to parameterize basically strength or material properties that are often used in process-based models. So the more models you have, or the more processes that you're considering in terms of a chain of cascading hazards, the more inputs you need, material inputs in particular. For example, if we talk about earthquakes and landslide dams, if you want to model a co-seismic failure, one of the inputs you're going to need is shear strength. If you want to look at mobility of that landslide, you're going to need some shear strength properties that dictate the rheology or the runout of this failure. If you want to talk about, if so you have a landslide dam form and you're concerned about an outburst flood or the failure of that dam, you're going to need to know the strength of that landslide dam itself and its and the debris as it's disaggregated. In the end, what you need is material inputs for a lot of these models, amongst other inputs. So how do we get these shear strength values? Typically, one of the ways to do it is get in the field, get some measurements, maybe in situ, whether it's vane shear or CPT, or a variety of other techniques that give us a proxy or an idea of the strength that we have on site. The problem with that is that you need access, and particularly following natural disasters, that's not such a simple thing. Then, of course, there's lab testing, the cream of the crop, the best we can do. We can control the loading rates, we can control hydrology. However, when we take these samples back to the lab, one big question is how representative are they of the actual conditions in the field and the heterogeneity and at the scales of a big landslide, for example, which might have discontinuities or things not captured in that sampling process. And then there's inverse analyses, perhaps using topographic data or remote sensing data, which in the end smear strength values, but allows us to have a simplified and effective means of parameterizing the heterogeneity and the distribution of strength values at a larger landscape scale. So in geophysics, inverse analyses have long been used. We often see what's happening at the surface or maybe the near surface. And what we have to do is think backwards about what controls these processes or what inputs allow us to replicate what we observe in nature. One challenge of these inversions for landslides or inverse analyses of slope stability is that often if we're talking shear strength, there's an indeterminacy or non-uniqueness of the strength parameters that we're concerned with, whether maybe the most simple being cohesion and friction angle. It can be any combination. Nonetheless, there's been some great work that's used in versions to look at a variety of geophysical processes. For example, mountain weathering, the influence of earthquakes and how earthquakes might change weathering processes. We've also used this to look at relationships between landslide size, strength, and the state in which it's emplaced. So in the end, at least simplistically, consider this. What we have is a digital elevation model that has an inventoried landslide. Perhaps we have a headscarp mapped, we have the landslide topography, and what we have with the headscarp or the surrounding terrain is effectively topographic signatures that tell us something about the rupture surface of the landslide. We can project that headscarp. We can use the boundary conditions of the unfilled terrain to fit a rupture surface. We can also use the surrounding terrain to reconstruct a source zone of material in the case that the landslide is not completely evacuated. That gives us an idea of maybe where the landslide started and where it is now. When we have these three data sets, what we can do is use 3D slope stability and back analyze, for example, the landslide deposit for the frictional strength, the residual strength, and then use that strength to back analyze the peak strength from the source zone itself, whether it be a cohesion or peak friction angle. And what we get is strength, but we get a variety of things from this analysis. For example, this was run on about 7,000 landslides here in the state of Oregon. And what we see is that, well, we have certain distributions of landslide size, volume, and areas, and they follow trends that would have been observed in the literature, although there's certainly censoring based on mapping. We also see that given these three-dimensional surfaces and these volumes we get, we see that landslide area and volume scale, as they should, has been observed for lots of landslide inventories here. And we see that this inversion gives us reasonable estimates for volume given these landslide areas that we can measure from the surface. That's useful, at least as a byproduct. For example, the source volumes we reconstruct for an individual landslide are valuable for runout analyses. People who do runout or mobility of landslides often have to make an educated guess about the source zone of the landslide, particularly in the case that it's not completely evacuated. When we take the strength properties and generalize it over the landscape, we can plot a failure envelope that relates mean effective stress and shear strength at the landscape scale. And what we see is a non-linear failure envelope. This might seem a bit strange, but it's something we observe in rock mass, as well as in soils where we expect dilation and a sensitivity to basically normal stresses. We also see a trade-off in magnitude of cohesion and friction with landslide thickness, which is a signature of weathering and stress dependency. So for example, here, if we look at the proportion of strength as a function of landslide source thickness, we see that there is a trade-off between friction and cohesion, although it's gentle. And we see that that generally matches an area where we see the largest distribution of landslide thicknesses, although there's most definitely some small landslides missing here. What this suggests is that this increasing proportional cohesion with depth reflects more intact rock mass and effectively less weathering. It's a signature for that. And we can use this to quantify damage at a landscape, with damage with depth, as well as the preconditioning potentially for different hazard cascades that stem from landslides or other processes dependent on shear strength. What we also get are basically shear strength distributions as they relate to lithology, for example, or different types of mechanisms. A lot of landslide susceptibility models focus on one specific mechanism, but here you have an opportunity to look at different mechanisms. It can be used in predictive process-based hazard cascade models, and there's a variety of those out there, some of which will be talked about today that are excellent. In the end, though, these process-based models need strength as an input. And of course, can be used in landslide mobility or landscape evolution modeling. The volumes, the geometries we get here, the strength values, these are inputs needed to parameterize basically models looking forward in time. With that said, I'm all done. Thanks for having me.
Thank you, Ben. Excellent talk. Lots of interesting stuff here to discuss. And I think the last slide connects well with what Nick Sitar will present also. So
Cool.
That's awesome.
Thank you.
So the next, yeah, absolutely. The next speaker is Nick Sitar from UC Berkeley. I think he's from the Department of Civil Environmental Engineering. Nick, I think you can share your screen.
Yeah, let me see if I can get myself into the right space. Okay, so just following Ben, Ben looked at the sort of general approach to modeling landslides on a regional scale, and I think that's really important. The problem is when you become, when you actually have to solve a problem, then you have to look at how you can analyze a local specific situation. And so I have been looking at more efficient modeling of particularly rockfall type problems. And let me just see. What I'm going to do here is start with this. This is the motivation, is this little video from, I hope everybody can see it. This is from County Sheriff in San Bernardino. And it shows a rock slope and a rock failure. And if you look at it, this is perfectly dry. It's disaggregating and it's flowing. Now, I'm going to talk over these people, but you'll see it. These kinds of failures are often modeled as fluid flow, and it certainly looks like fluid flow, but as Ben said, then you have to, and previous speaker said, then you have to come up with some parameters that approximate the rockfall as a fluid flow. But as you can see, it's a bunch of individual particles, they're very large, rolling down a channel and interacting with each other. And so the question is there something that we could do about this? And so I'll just go to the next. And so, you know, people have done a lot of these. You can do individual rolling boulder simulations using combination of physical process modeling and then empirical analytical trajectory assumptions. And there are many of them. I'm just using one example, the Rocky 4 3D. I already mentioned equivalent fluid simulations, computational fluid dynamics. More recently, people have used material point method, but it's an equivalent fluid. And then, of course, there are many empirical runout relationships, and you can back analyze slopes the way people do for regional. And I think Ben showed a really nice way approaching that kind of a problem, but it's empirical, and empirical is great. There is nothing wrong with it. The question is, can you do something more specific? So we were working on a completely different problem, actually, to start with. We were trying to model triaxial test in sand using DEM. And in order to do that, we had to do a flexible membrane. And it turns out there are a lot of papers out there that people say they did it. It turns out not to be so easy to do. And as a result, we also looked at, is there something else that we could do? And we came across an impulse-based DEM, which is quite efficient mathematically. And as a result, it's efficient in computationally. And then one can actually model the actual block shape and the terrain and take into account rolling, sliding, and ultimately breakage. And so it's a fast, efficient method. And what I'm going to do today just show you some proof of concept type simulations. So here is a set of is a rock mass. It's just a series of irregular grains on a topography from a DEM. And I'm just going to start this. Let's see, and let it flow. And those of you who do DEM would look at it and say, you know, am I using, how many cores am I using on what machine? This is done on a laptop, just so you understand the efficiency of it. And here is a slightly different configuration where the surface on which the flow runs out is inclined. And this was motivated actually by my work back on Denali earthquake, where we saw the landslides flow out to the glacier and then follow the glacier. And clearly we can do this as an illustration, okay? If you're interested in the actual formulation, I have the reference here, which I'll then post as a PDF. So the point is that we can now model very efficiently runout of granular flows without making any assumptions about viscosity or anything else. These particles just have irregular shapes and they have frictional properties, purely frictional. And let's see if I can now get into the next slide, which seems to be a challenge. Okay. The other problem is, can you put in a flexible barrier? And so let me show you, because ultimately, let me just get on this. Ultimately, you want to protect a structure, usually a roadway, but maybe another structure. And so this shows a bunch of particles falling into a net, which, by the way, I many years ago saw a demonstration like this with a car underneath the net, and it worked. And so let me now, my mouse is a bit of a challenge here. Let me see if I can find it. There. And then we can do this kind of a thing where you have a net and the rock mass is falling into the net. And is, in this case, the net actually gets breached. But you can see that this has many different applications. In this case, we just use a flat surface. For this presentation, we have a bunch of other simulations, but for this presentation, I thought this would be sufficient to basically show the potential of a technique like this. Now, in this case, this thing does funny things. Let's see, let me, if I get my mouse out of this. Yeah, here we are. The point is that we can model actual 3D falling block geometry. We can start with a 3D shape. We can represent it quite efficiently. We can incorporate this kind of, since it's a very efficient code, we can incorporate stochastic processes so that initial orientation of the block, initial shape of the block can be modeled. And we can then consider different types of barriers. Now, there are people who have done analytical work on barriers, rigid and flexible, but in this case, we can consider all types without making empirical assumptions. And that is the ultimate goal, that as far as I can see, we can now develop methodology and codes that could be used for site-specific assessment, which is different from doing regional assessment. And so this is really the focus of this work. So thank you very much.
Thank you, Nick. This is great stuff. Very good to see the progress here, and you're bringing us into the consequences and the mitigation, which is great. So the next speaker is Dino Bellugi from the Earth and Planetary Science Department at UC Berkeley. Dino? Okay, great. Thanks. You want to share your screen?
Yes. Oops, going a little ArcGIS problems. I wanted to start by thanking all the organizers and conveners, and importantly, the participants, and also clarify that I'm now in the Department of Geography at UC Berkeley. So you may find yourself walking around your favorite regional park, like Black Diamond in this case, here in the Bay Area. And you may find yourself there, like Kirkcaldy did, shortly after a big series of storms like the one we had early in California this year. And you may find yourself looking at a series of scars of landslides. And you may ask yourself, why are they where they are? Or why are they the size they are? And you may ask yourself, how did I get here? And what can I predict about this stuff? So today I want to present to you a discrete shallow landslide model that predicts landslide size and location, and it's being coupled with models for critical zone structure and subsurface hydrology that we've heard things about today and yesterday as well. Oops, I'm not going presenter mode.
Yeah, I was going to tell you that. Thank you.
Presenter mode, there we go. So first, let's think about how do we represent a landscape like we saw in the previous picture in a 3D digital world. Well, we can discretize the landscape as a series of cells, each one representing soil columns. And we can see here an example landscape with some landslides on it, sort of like we saw in the previous pictures. And we can apply a slope stability model. In this case, the model developed by Milic et al. In 2014, which can assess the stability of landslides by performing a force balance and considering resistive and driving forces and earth pressure forces and root strength and that sort of stuff. And this model takes in elevation, soil depth, water table height, root strength, some material properties like friction angle and soluble density. And it's been recently modified by Dave to also account for non-slope parallel seepage forces, which are very important for to represent exfiltration processes in a fashion as described by Emerson and Major back in '86. So I want to stress a couple of things. We are talking about just shallow landslides. We are assuming a limit equilibrium framework. So we treat this as a rigid block. And another big assumption is the failure plane location, which is typically located at the interface between the soil and bedrock. The problem that we have at hand is that we don't know which of these cells will end up being a part of a landslide, will become landslides together and mobilize. So how do we search the landscape for clusters of these cells is a difficult problem because there are many combinations of cells that we have to explore to do that and making the problem intractable. So we found a way to get around this by representing the landscape as a graph where the nodes of these graphs are correspond to the soil columns that we saw before and are annotated with driving forces that those soil columns can contribute to a landslide. The edges instead represent the resistive forces that can develop between these soil columns. And so what is a landslide in this world is just a collection of cells which can be represented by an indicator, a binary indicator vector, or where is 1 means you're inside a landslide and 0 you're outside. If we write those resistance and forces that we talked about before in matrix form, then that factor of safety computation becomes a matrix operation shown here, and the quote unquote optimal landslide would be the one where its indicator vector minimizes this expression. So we have a fast way to compute the factor of safety, but we have still a problem at hand that minimizing this expression in the discrete binary world is still an intractable problem. Thankfully, there's a way around this called spectral relaxation. So if we let this vector x, instead of being just 1s and 0s, take on real values, we can rewrite this as a linear system that we know how to minimize. And the minimization is obtained by looking at the eigenvector x star, I'll call it, that is corresponds to the smallest eigenvalue of this linear system. This was inspired by a pioneer work of Shi and Malik in 2000 here at UC Berkeley in the field of perceptual grouping and image segmentation. And while very, very different, because this is based not on resistive and driving forces, but some measures of picture similarity and distance between pictures, they showed that these eigenvectors obtained by the method that I just outlined point to coherent parts of the image that can then be used in the process of segmentation and identification. In the case of landslides, these eigenvectors instead point to specific parts of the landscapes, which are the places, they're exactly the places where we expect landslides to happen, steep converging places in this example. So to recap, we have a model that takes a series of inputs, topography, soil depth, root strength, pore pressure, and seepage forces, and material properties. And I should say that these are not easy to get, and so are often modeled. Then a slope stability model is applied to each cell in this digital landscape. We run the search algorithm, and we output a set of discrete predicted landslides. we tested this model in a site near Coos Bay, Oregon, that was extensively studied for a period of 10 years and instrumented. And as inputs, we used lidar-derived topography, soil depth that was a result of a regionally calibrated coupled soil production and diffusion model, and then root strength, which came from individual site measurements, but then was modeled on the entire site as an exponential function of depth. And to get a pore pressure field, we used a simple variable contributing area hydrological model that just assumed shallow slope parallel subsurface flow. The output of this model is then a set of discrete landslides that are shown in red, and I stress that these are individual landslides with a shape and a size associated to them. And these matched, many of these overlapped with mapped landslides that were mapped by researchers over this period of 10 years. We can also see that the overprediction that is typically associated with the infinite slope cell by cell method shown here in purple is greatly reduced.
Dr. Bellugi, or at time.
Oh, okay. Well, I'll finish by saying that slope parallel flow is not the only flow. We know that the critical zone changes and generates a variety of different runoff mechanisms. And so to look at the whole picture, we can look at models like Solgi showed us yesterday of critical obstruction and couple them with a model like the one that Giuseppe presented that is capable of predicting fluxes and pressures. And then couple this with our model and start asking questions like what controls the structure, how does water move through it, what kind of pressure fields, and what does this mean for landslides. Solgi showed us yesterday some preliminary results that we'll come back and present, showing how the different type of critical zone structure affect landslide size and location and localization. Thank you very much. Sorry for going over time.
Thank you very much. Very interesting presentation. Sorry, if you can hear me. Thank you very much for the excellent presentation. We'll move on to the next one. I think in the next presenter is Dalia Kirschbaum from NASA, and because the last moment she couldn't make it, we have a recording for her, and her collaborator Thomas Stanley is here also to participate in the discussion. Maybe Adriana. Yeah, thank you very much.
Thank you for listening to this presentation. I would like to take you through some of the work that our team has been working towards in advanced multi-scale landslide hazard assessment, primarily leveraging remote sensing data. And want to acknowledge our entire team who have put this together. So first, to put this in context, we are looking at this both from a multi-scale and a multifaceted approach, and that includes local and regional mapping, regional and global modeling, and then looking at the impacts dimension, so exposure modeling and forecasting, looking from days to even decades into the future to see how we can better understand and constrain rainfall-triggered landslide hazards in different contexts. So first I wanted to start with the mapping aspect of this, and so one of the key features is how can we rapidly, with a decent accuracy, assess where and when landslides are happening. And so this is an example from an event in Vietnam where we used an algorithm to better understand and map polygons of potential landslide activity. And we do this with what's called the change detection-based SALAD algorithm. And this is from my colleague Bukharamatya and his team. And so using a random forest model with high resolution commercial imagery, for this specific study, he was able to map over 20,000 landslides from different events across Southeast Asia. And he's used this to look at events from other locations as well. So one advantage to this is that we can look over time, so create that multi-temporal view. And so this is an example of the Arun River Basin. And so you can see over the last 10 years, he was able to construct a view of where rainfall-triggered landslides, or landslides in general, are occurring in this basin. And this was helpful to inform hydropower projects for the World Bank, where they're looking to understand the geohazards associated with those areas. Now this algorithm is open source and is also being worked on to evolve to use for Google Earth Engine. And it can be used with optical data that is freely available, such as Sentinel and Landsat as well. So moving on, we developed inventories from around the world, as well as brought together multi-temporal inventories to advance our landslide hazard algorithm. We call it LASA, the Landslide Hazard Assessment for Situational Awareness version 2. And this couples some static factors with real-time triggers, so focusing on near real-time and antecedent moisture, as well as soil moisture from satellite assimilated modeled products. And then looking at a forecast as well, which is new to this capability. So looking at a 24 to 48 hour forecast, as well as additional exacerbating impacts such as debris flows. We're also working on kind of the seismicity. So after an earthquake, how to represent the destabilizing impact of an earthquake, but that's still ongoing. So using a methodology called XGBoost, which is a machine learning algorithm, and then inventories from around the world, we use that to train and then evaluate a new model. And with it, it was able to provide a suite of products. So this includes a relative probability of a landslide hazard, as well as a forecast within a couple days. And then we're also able to use to develop an exposure model. So Thomas Stanley developed the LASA version 2 with help from many colleagues, and Robert Emberson worked on the exposure modeling capabilities. And so this helps us to better understand, where populations potentially are impacted, as well as critical infrastructure and roads. So when you run this over time in the past, we can get a set of mean landslide predictions, really understanding the spatial variability of the relative probability of landslide hazard for rainfall triggered events. But as I mentioned, some new activities are with a forecast. And so this is on the left shows an output from our SALAD algorithm. And then on the right shows where we put in a global forecast. So this is from the Global Modeling and Assimilation Office. And so this forecast helps us to understand kind of the 1, 2, and 3 days prior with the nowcasting. And that precipitation data is from the Global Precipitation Measurement Mission. Now, what we found is that this type of forecast does reasonably well for large events, but still suffers from trying to pick out individual kind of intense, short duration, high intensity events in a landscape that also may trigger landslides. The other aspect of this model that is new is a post-fire debris flow module developed by Eli Orland and team. And so it uses a similar regression model to that of Staley et al. In 2016, and then develops essentially a basin-wide representation of potential exacerbating areas for post-fire debris flows, using several different remote sensing inputs to characterize. And so this is just an example from in Australia, where we can understand where, if you look at the output probability, you can see that value as the dotted line, and then the precipitation inputs, and then known landslides as well. So this is just being incorporated into our version of the model. Now, the loss of framework, and more generally, we have a version 1 and version 2, have been used with different stakeholders. So one is the Pacific Disaster Center, and so they actually use LASA, it's going to be going live very soon, to understand landslide hazard threats around the world, potential threats and impacts. And so they have developed a system through their disaster aware system to incorporate the landslide hazard model, the LASA model, within their framework. And then they also are able to extract the impacts using their own exposure tools. At a regional scale, we've been able to work with regional stakeholders such as Southeast Asia to understand potential regional hazards. So this is work done by Nishan Biswa from our team, and developed a regional version of LASA in the Mekong. And they use their own interface to highlight potential areas of landslide hazard. You can zoom in and better understand impacts. And then lastly, this is actually version 1, has been developed operationally and is used in Rio de Janeiro. And so this is the operations center that uses this to highlight where landslide hazards may exist around the city based on rainfall, and what infrastructure and road networks may be impacted. So just to close, I want to highlight that all of the code is freely available and open source in GitHub, and you can access all of this through landslides.nasa.gov. There's also a viewer that has information about impacts in near real time at a district level. And we always are in need of more data, so if anyone's interested in contributing to a citizen science-based project on this, again, please go to landslides.nasa.gov to access Landslide Reporter. And with that, I just want to thank you and wish you a really great meeting, and my colleagues will be happy to take questions.
Sounds great. Thank you, Dalia and Thomas, also for being here and participating in this activity. We move on with the next speaker. The next speaker is Katy Barnhart from USGS.
Can you hear me and see the screen?
Yes, absolutely.
Great. Okay, so I'm going to talk about debris flows and landslide runout simulations for post-fire and tsunami hazard assessment, which could also just be called DCLAW. And you'll see here in this second slide that there's a bit of an expanded author list that reflects the main folks who've contributed to this effort. And I think, as you'll see as I go through this, I'm mostly presenting work that was done by people who are not me. So I'm going to talk a little bit about what DCLAW is, where it came from, what some notable features of the code are, and give example applications that include past events and hazard assessment for events that have not occurred. And I'll conclude by a few things that DCLAW is not. So DCLAW is a depth average geophysical fluid dynamics model that simulates the coupled evolution of fluid and solid phases while satisfying mass and momentum conservation. One of its state variables is solid volume fraction, and when it has high solid volume fraction, the material behaves like what we might call landslide material, and when it has low solid volume fraction, it behaves like a fluid. The theoretical and numerical implementation are described in the two papers shown on the right. These are the equations. I will not go into them in detail. So like I mentioned, DCLAW represents the landslide as sort of, it conceptualizes it as fully saturated granular material. That material has thickness, velocity, and solid volume fraction. Those quantities evolve through time and space under the influence of gravity. I will not discuss how DCLAW is parameterized in detail, but I'll just say that the sort of mobility of the material is controlled by the evolving solid volume fraction and evolving pore pressure. And this cartoon in the upper portion of the right-hand column sort of is a reminder that this is a depth average model. So there's no sort of landslide material going underwater, but we're dealing with sort of depth average quantities. DCLAW is an outgrowth of the CLAWPAC family of codes that are based on algorithms for solving hyperbolic systems of equations, and specifically the GeoClaw software developed for tsunami modeling. So what are some features? One of them is adaptive mesh refinement. This allows for the simulation of problems across a wide range of scales. The computational resources are focused on an area of interest. DCLAW and the other sort of GeoClaw related codes use well-balanced methods, which are important for things like tsunami modeling and reflecting a flat ocean over very complex topography like that is shown here from a tsunami application. DCLAW uses shot capturing finite volume methods, which are important for effectively representing discontinuities and hydraulic jumps, especially over irregular topographic features like this example that's shown here. And then in DCLAW and in GeoClaw, there's a natural wetting and drying of cells, which allows the shoreline to evolve naturally and simulating inundation. Here is a, I think, pretty impressive application of GeoClaw to the 2011 Tohoku earthquake and tsunami. And you can see in this right-hand column the matching of the wave height and wave velocities in the harbor in New Zealand. An application of DCLAW to past landslide is this one here, taken from work by Dick Iverson and others, looking at how different material sort of mobilities are reflected in sort of different behavior in DCLAW in the context of the 2014 OSO event. Another example from a past event was led by Dave George, looking at the Tyndall Glacier landslide and Tan Fjord tsunami. And on the left, you can see a animation of the simulations, and on the right, you can see that the model matches well the inundation extent observed. I have applied DCLAW to a number of post-fire debris flow applications recently, focusing on building damage. And so on the left, you can see the pattern of building damage that was observed in that event, and on the right, the probability of having building damage, and it does quite well. I've also applied it for hazard assessment to the Barry Arm landslide, which was the subject of an open file report published by the USGS. And in the center, you can see some example output of water level through time. Dave and Dick and others have applied this for hazard assessment to the Mount Rainier, Lahar hazards. So we can see an animation on the left, and then an example of inundation in Ording, Washington, in the center. So I'm going to conclude with a few comments on what DCLAW is not. DCLAW is not a 3D model. So landslide material doesn't formally go underwater. It doesn't go under bridges or, through culverts. It's also not a slope stability model exactly. A user must specify what can move and what can't. And then given that specification, slope stability is evaluated. It's not a model for all type of mass movements. There's a very specific conceptualization of what the landslide material is and isn't. And it's not GUI. It's a Fortran code with a Python wrapper. So with that, I am looking forward to the discussion.
Thank you very much, Dr. Barnhart, about this very, very interesting presentation. It's great. I think we're covering lots of different ground here, which is great. The next presentation is by David Millage from Newcastle in the UK. David, thank you for presenting. It's probably getting late for you.
Hi, everyone. Hopefully my presentation should be on the way.
You can see your screen.
There we go. Okay.
Yes.
Okay, great. So I'm going to talk to you about detecting landslides, predicting their hazard, and communicating that hazard. And so first, in terms of detecting landslides, we know that big landslide inventories are expensive and time-consuming to create. But the big surprise to me was how inaccurate they are. Here we compared published inventories for the same trigger event. So 2 inventories for the same trigger event for 5 events from the really nice USGS repository of co-seismic inventories. All these were mapped by hand from satellite data. And in the 5 cases that we looked at, we found 8 to 30% overlap. That means that overlap is the percentage area identified in either inventory that was identified in both inventories. And the map on the left that shows the Wenchuan, a patch of the Wenchuan earthquake, gives some examples of what that looks like in practice. So there's probably lots of reasons for the mismatch. That could be mapper choices. It could be registration errors. I want to emphasize this isn't a few bad inventories. This is a random sample. We'd be kidding ourselves if we thought this wasn't a problem in our own data too. What it means is we need to think carefully about inventory error and its implications for how we use the data. Some better news then, there's been this massively increasing volume of accessible satellite data, and that's allowing us to examine stacks or data cubes. And that's really where my first kind of model for the Model Expo comes from. So this is just one example of what you can do using these stacks to find landslides. So for each pixel, then we get a time series of NDVI vegetation index. In this case, we can look at that before and after a known trigger, and in our case, use that to account for seasonality. You can then aggregate those different metrics for an individual pixel, combine them to give some indication of the likelihood that that pixel was part of a landslide triggered at that particular date. In my case, that's something we've called ALDI. It uses Google Earth Engine. The code is available on GitHub, and there's an app that was fairly easy to generate in Earth Engine as well. When we test that, we go to those same 5 places, and the fact that we have 2 overlapping inventories means that we can evaluate the performance of the manual mapping and compare that to the performance of the machine, the automated detection. What we find when we do that is that it's about a 50-50 split in the machine outperforming the human in terms of landslide location versus the human outperforming the machine. That detection algorithm was problematic because it needed 2 years of post-event data, which meant it was useful for research but not for response. It's also fairly coarse, 30 meters. That's driven by the Landsat. We've now been working using Sentinel data and a slightly different algorithm, which allows us to evaluate shorter wait times and smaller landslides, which is what we're looking at here for a cyclone in New Zealand, recent cyclone in New Zealand. Radar gives us the opportunity to look through cloud, and here we know that patches of coherence breakdown can be used to identify landslides. So in this case, we developed a series of coherence-based classifiers, which work really quite well at getting a general picture for landslide density. The hot colors on the left in each case, the classifier, and the cool colors, the observations of landslide density for 3 sites. And the key thing here is that because you can see through cloud, you can get those results much faster, 15 rather than 55 days for this Nepal example. So then hazard maps, these are currently the primary format for communicating landslide hazard. But when we've talked to people on the ground, we tend to find that the maps are difficult to access and difficult to interpret. And so as an alternative to that, we've been trying to come up with simple rules. And this first rule is to minimize the hazard area. That's the upslope area steeper than an initiation angle that runs out over a slope always steeper than a second stopping angle. And I'm illustrating that with the picture on the left, where we can see a very steep area upslope of the white arrows, and that area runs out down a flow path that's always steeper than about 15 degrees. So that would have a very large hazard area. And we can test these rules by implementing the metric for every cell in a DEM. A second rule that we've come up with is this skyline angle, and that's the maximum look angle from horizontal to the skyline. Again, it's a metric that we've tried to come up with to account for runout, because we see runout as one of the missing components in many of these hazard analyses. People tend to focus on initiation. Runout generally isn't so well represented. And again, we can implement this in every cell across the landscape to test it. So we've done that for a series of large earthquakes, 6 large earthquakes, and also for 8 storms. And when we evaluate that in terms of the area under an ROC curve, so some performance metric, we find that the hazard area does really quite well, does best, and does really quite well for earthquakes, both hazard area and skyline angle, less well for rainstorms. And when we compare this to hazard models, what we find is that the models tend to outperform the rules, but not by much, and not always. It's worth bearing in mind that, so here we're looking at earthquake-triggered landslides, that these models all use peak ground acceleration or some shaking intensity, which is something we wouldn't have ahead of the event.
Mr. Millett, you are at time.
Okay, so the same for rainfall. We see a similar story. The rainfall scale is slightly lower, but the models themselves are also slightly lower. And the gap between the 2 green stars here is the difference between ShallStab, a model that's just initiation, the poor performances, and ShallRun, a model with a very simple runout prediction, the top set of stars, which highlights how important it is to put even a simple treatment of runout into your models. And I'll finish there.
Thank you, David. This is great stuff. A bit disheartening, but great. Okay, the last speaker before we get into the conversation and discussion session is Alex Gore from the University of Arizona.
Hi, can everybody see my screen?
Yes, you can. You want to put it in presenter mode?
Yes. Is that good?
Yeah, looks great.
Okay, thank you for having me. My name is Alex Gore. I'm a PhD candidate at the University of Arizona. And today I'd like to talk to you about a reduced complexity model for debris flow inundation that I've developed with my colleagues. And specifically, I want to talk about it for use in rapid hazard assessments following wildfire. So I'm sure most people here are familiar with post-wildfire debris flows, especially since we've already had several talks on them. But they're fast-moving mixtures of water and sediment that occur in steep watersheds, and they are particularly prevalent in watersheds that have been recently burned by wildfire. And as several other speakers have mentioned, wildfires are becoming more frequent, severe, and large across the Western United States. At the same time, more people are moving to the region. So as a result, more people than ever before are being put at risk to these hazards. We touched on this event several times today, but I'd like to highlight once again the 2018 Montecito debris flows that occurred in Southern California following the 2017 Thomas Fire. As we can see from these images, these post-wildfire debris flows had a severe impact on the downstream community of Montecito, damaging over 400 homes and resulting in over 20 fatalities. And this really underscores the necessity for having a well-established framework in place that can be used to mitigate the future impacts of post-wildfire debris flows. So when we're considering hazard assessments, we might ask ourselves a few questions. The first being, how likely is a debris flow to occur in a given watershed given a certain rainfall intensity? And then how large might that debris flow be? Now, these two questions are addressed by well-established methods. There's a debris flow susceptibility model and a post-wildfire debris flow volume model that are widely employed in hazard assessments in the Western United States, including by the USGS and their post-fire hazard assessment. But today I'd like to focus on this third question, how far? Most hazard assessments currently don't employ debris flow runout models for a variety of reasons. Some might be that a lot of established debris flow runout models are pretty computationally expensive, or they might require a number of parameters that are difficult to constrain prior to an event, especially in a scenario where time is limited, such as between the containment of a wildfire and the onset of debris flow producing rainfall. So as a result, our ability to predict the downstream impacts of post-wildfire debris flows is limited. To address that gap in knowledge, I'm going to present on a reduced complexity debris flow model that we have developed called ProDF, or the Progressive Debris Flow Routing and Inundation Model. Today, I'm not going to get too into the weeds about how the model works, but if anyone's interested, I'll point you in the direction of this paper that we published last year as a good place to start. Coming back to the Montecito debris flows, I'm just going to introduce ProDF through the lens of this event, primarily due to the comprehensive data that's involved here. In the days following the event, a team from the USGS traveled to the site of the debris flows and got really great detailed information about the extent of inundation, shown here by the hashed polygons, as well as debris flow volume and peak flow depth data. Now, when employing a model in a rapid hazard assessment scenario, it's really important that it doesn't require too many parameters that are difficult to constrain. So ProDF only requires a handful of model inputs, the first being topography. So this is just a pre-event DEM from the Montecito study area. Second, you need to provide the model with starting points. So this is kind of like an initiation point. It doesn't really need to be where you expect the debris flow to initiate. Most post-wildfire debris flows do not have a discrete initiation point anyways. It really just needs to be upstream of where you expect deposition to occur. So for this Montecito example, we simply chose the upstream extent of our pre-event topography, shown here by the red dots. You need to provide the model with a debris flow volume, and for reasons I won't get into here, that's notoriously difficult to constrain. But if you're using it in a predictive sense, you can use the debris flow volume model that I touched on earlier. Or in this case, where we're calibrating to an event that already occurred, we simply used observed sediment volumes, which are shown here. And then finally, you need to provide the model with 2 flow mobility parameters that need to be calibrated to the site. We're working on a framework so that these are already constrained and the model can be used in a predictive sense. But at this point, you still need to calibrate to a local example before applying it in a predictive sense. Given that information, ProDF outputs 2 primary pieces of information, the first being the extent of inundation. So in this example here, once again from Montecito, we see everything that's in color from blue to red has experienced some flow throughout the course of the simulation. And then second, it provides information regarding peak flow depth. So this is really important information for identifying which areas are the most susceptible to the most severe impacts of post-wildfire debris flows. So in this example, areas that are in cooler colors are areas that experience lower flow depths, and those in warmer colors experienced higher peak flow depths. If we just look at the model, how it performs, just looking at extent of inundation, we can see this is how the model performs when calibrated to the entire 5 watershed data set. Areas in blue are areas that are reproduced accurately by the model, while areas of gold and gray are areas of model overestimation and underestimation, respective to observed extent of inundation, respectively. I'd just like to highlight here that model efficiency is also critical when modeling over larger regional scales, especially in a short time window. So running this 40 square kilometer study area on 5-meter input DEM on just a standard laptop computer, ProDF runs this simulation in approximately 30 seconds. So, you know, reduced complexity and efficiency make this a promising tool for post-wildfire hazard assessment. If we just look at peak flow depths here, we see that the model in this scenario does pretty well, reproduces 80% of observed peak flow depths within a meter and 30% within 20 centimeters. So we are currently collecting inundation data from across the Western United States to calibrate the model and try to observe any trends between the flow mobility parameters that I briefly mentioned that need to be calibrated and region climate, geology, watershed morphology, so that we can employ ProDF in a predictive sense. And with that, I appreciate you having me.
Thanks, Alex. Very interesting work. Thank you. Thank you. A great presentation. All right, we have thank you all the presenters for your presentations. I think like the previous sessions too, we had a very wide range of approaches to complex problems, and it's interesting to see how different groups have tackled these issues. The there is lots of things to discuss for sure, and I can definitely bring some topics up. But I wonder if someone wants to raise their hand and ask a question to. And if you go to the spreadsheet that the file that we've been using, you will see lots of questions there. I guess one thing that to me comes out when I see all the presentations together is how do we get the input for these models, and what are we missing? I heard lots of things even from David's presentation about maybe the input that you use or you're calibrating against is not correct. But in general, what are the gaps in your modeling efforts? Maybe for each of the speakers, from what you modeled, what is the single most important thing that you feel this is probably the worst of all my inputs? If anybody has any feedback on that, I'd be very interested to hear. Is it the DEM? Is it the subsurface properties? Is it the climate? Is it what?
So this is Thomas. I would say that the subsurface is essentially unknown from my perspective. It's the DEM is actually very good. We know pretty well what the surface is, and like the atmospheric stuff is kind of intermediate between those two.
I think I would go so far. I'm going to lump a few things together, and I'm going to say the things that contribute to the size. So the magnitude of an event, I'm going to put first. So that could be everything in the subsurface and also potentially the DEM. And then secondly, everything that goes into how mobile something is, which, you know, may depend on the type of landslide.
Yes.
I could add to that the other things, as mentioned, the subsurface properties are not just the conductivity of the subsurface and the strength, but there's also fractures and preferential flow that are hard to know, even though people like Roman DiBiase's have started looking at ways to map out fractures. Another thing that is extremely variable is soil depth, which is really important for landslides. And that is actually very heterogeneous. And models like the ones we use sort of give you a loaded version of the landscape that doesn't consider what the biological, a specific site, place may look like, or the effect, the history, the legacy of previous landslides. Another thing that I'll add is root strength. We modeled root strength. Kevin Schmidt started doing work back in 2000, digging pits and looking at root strength. And then Josh showed how these fields can vary by distribution of trees. Groups like Schwartz and Noor at ETH showed that, you know, these things don't break all at once, and there's like and they propose a fiber-bundle model. These are all things that can affect, and they're really hard to know, and it can affect landslide timing and location. Additionally, we also showed that the sort of area, the spacing between all these things is important, like the correlation length that is you can associate at each of these fields, and their interaction is also important for defining size.
Great, lots of good feedback. I'm taking notes at the same time, but yeah. Any other thoughts on that?
Yeah, I'll follow up on that just briefly. Groundwater. I mean, the groundwater conditions, particularly those antecedent conditions associated with a triggering event. Also, I think one big opportunity is better coupling of the slope stability models with the runout models. It always feels like two silos, and there's a lot of great models out there, but one of the big things, one of the big gaps to bridge, if you will, is making those models talk to one another and parameterizing it.
No, yeah,
I'd say for earthquakes, at least we do surprisingly well with just topography and just slope. So, I mean, that could either be really encouraging or really depressing. In that you you can get a pretty good prediction of where earthquake-triggered landslides are going to initiate from the inclination of the ground surface on its own. And then if you add some very simple treatment of the runout, then you do well in terms of these kind of spatial skill metrics at reproducing the footprints of landslides.
Great, David. I think that's a great point, and I'm curious if you have an opinion about why you think we're doing better in earthquake. Is it the timing? I think that there is issues that I have in mind related to the timing about what we map at the end, progressive failure of what we're looking at the end.
It could be. I think so what I didn't say was this analysis was done at 30-meter resolution, and I think either the landscapes that we picked for the earthquake-triggered landslides, or the difference in process where you've got topographic steering of the groundwater. So it may be that finer resolution topography is more important for capturing the spatial locations of the rainfall-triggered landslides. The only case where we had good performance of the rainfall-triggered landslide models was in the Colorado case, and in the Colorado case, we had clear. It was a landscape where there was clearer kind of topographic forcing to the locations of the failures.
If I may, I think the challenge here is that we cannot use one model for everything. And one has to start looking, because we have the computational tools, we have the remote sensing tools, to start parsing these different processes. Shallow landslides, very shallow debris flows, don't really care much about bedrock, but a little deeper debris flows with shallow soil cover actually are fed by bedrock. It's not surface infiltration. It's a completely different process. And there is data to support it. There is actual field data. Number of people have instrumented sites. We did one of the first a long time ago, but people have done it since. Same thing for seismic. And the other thing to look at is we really have to consider site-specific meaning regional, okay? South Island of New Zealand, the Alps, a very different setting from, let's say, the Wenchuan earthquake, which are also very tall mountains, relatively hard rock. So I think we have an opportunity to start applying these tools to more site-specific. And ultimately, we have to look at really specific, as I sort of implied. I've been involved in this since 1982 here in Bay Area. When we had a lot of debris flows, USGS, every time it rains, issues a debris flow hazard warning. If I'm a citizen sitting in my house, what am I going to do about it? Unless the local sheriff says, please evacuate because USGS says it's a real hazard, nobody moves. And that is the real problem, is how do we, in the end, come up with a way of forecasting with reasonable accuracy, so when people evacuate, something actually happens. You have this problem, cry wolf. If people evacuate, nothing happens a couple times, they won't do it. And in the US, of course, we have our special problems where people don't want to be told what to do in the first place. But the real issue is being able to make a prediction based on the best available data that is sufficiently accurate so that people, when they hear it, respond to it, because ultimately that's what it is. We want to protect lives and property. And how do we do it in an efficient way? So, it's still a big challenge, but I think we have a lot of tools that we can apply to it.
Yes, absolutely. Thank you, Nick. I think some of the stuff you're saying connects to the next sessions too. Katy, I think you had Dr. Barnhart, you had some comments. You've been waiting. Yeah, please go ahead.
Yeah. So I think this connects to what David and Nick said, and also one of the questions about probabilistic versus deterministic approaches. And I think the sort of cornerstone that I think we might benefit from focusing on is, for any application, we need to be formally saying, why are we doing this? Are we doing this because we're trying to understand a mechanistic landslides from a mechanistic way, or are we trying to make a probabilistic forecast for people to, evacuate? Or are we trying to decide whether a village should be in a location or not? And different applications need different sort of philosophical approaches. And I think we would be very well served by formalizing what those different reasons are and sort of making sure we're matching the tool to the thing and evaluating it. So to this question of, are analyses deterministic or should they be probabilistic? I think that depends on whether a probabilistic answer is needed. So
thank you so much. I think the comment of the objective of the modeling was great. Last question, we have Sukanta, and that will be the last question for the session because we ran out of time. Yeah.
Thank you. In recent, due to lack of horizontal ground, hilly areas, man-made structures, buildings, and tunnelings, lots of activities is going on. So those have really effects on the overall local stability of the slopes or any hills sites. So is there any open platform or any expert opinion this? Because in India, these are recent facing some of the sites, land subsidence and other things. So if any experts, any work that I would like to know.
Yeah, Sukant, I think this is a great point. I think you're bringing up the point that humans are altering the environment more than other processes. And this can open a whole other discussion. There was a recent paper about this, I think, that showed that there was a significant influence of the human activities on what we're seeing. I'll send you that maybe so you can take a look. But yeah, that's a great point. Unfortunately, we have to move on, I think. And I'll pass it on to my colleague Josh Roaring to keep going. Thank you so much for participating. We know this is not enough, but we're hoping that it's a good start. Thank you.